Okay, today I'm going to do 2018 AP Physics C free response question number 3. And so this one is taking our calculating moment of inertia with rotation or with calculus a little bit further. So you notice that they give us this and they say that it has a non-uniform linear mass density. Well, that linear mass density, that's what this lambda is nothing more than the ratio of, or the derivative of mass with respect to distance, x, the coordinate that we're given. So we've got 2m over L squared x. And we're going to use that in solving this. So on A, it says, using integral calculus, show that the rotational inertia about its left end is ml squared over 2. And I love when they give us an endpoint because they're kind of telling us this is your answer. You just got to get to that. So let's see what we can do with this. So the first thing that I remember when they say using integral calculus is I'm going to go back to that formula for I that says I is the integral of r squared with respect to mass. Okay, r being the radius, the distance from the axis of rotation that we're talking about. Well, these guys, their axis of rotation is at their end, and that r value, instead of being r, is going to be x. So we're going to change it up a little bit for r's, and so it's going to be x squared dm. Okay, so nothing different about r and x. It's just the fact of they're not calling it r, they're calling it x, and so it's the same distance from axis of rotation. So I need to do some subbing because I don't know how to integrate x with respect to mass. But that linear mass density that I just had, if I take that and I write that as dm over dx, and it's dm over dx, it's mass to length, so whatever terminology they put for your length, so x is what we're using this time, is equal to 2m over L squared times x. So what I'm going to do is I'm going to solve this formula for dm. And so I'm going to say dm is equal to 2m over L squared x dx. And that is what I'm going to put in this formula for dm. So I'm going to take and direct substitute that. So I is the integral of x squared times, and I'm just going to put a bracket around this so I can keep it kind of separate here, 2m over L squared times x dx. Because that's dm. Now, I'm not quite ready to integrate yet. I want to put my bounds on it. And I'm going to bring my constants out. Big M is the mass of the whole thing. L is the length of the whole thing. So those are constants. So they get to come outside. And then we're going to integrate x squared times x is x cubed dx. And now we need to put some bounds on our integral. So if my axis of rotation is here at the end, if this is my AOR, my axis of rotation right here, then I'm going to put my bounds as the amount of distance before that, which would be nothing, so that's going to be my lower bound, to the distance after that, which is going to be my upper bound, which is the length of the triangular rod. So now we're going to integrate this. So 2m over L squared, and then we're going to integrate x cubed. X cubed integrates to x to the 4th over 4. And we're going to evaluate that from 0 to L. So I get 2m over L squared times L to the 4th over 4 minus 0 to the 4th over 4. So we evaluated that with those two parts in it. So we get 2m over L squared times, this first one is L to the 4th over 4, and the 0 just goes to 0. Now I can cancel. I've got L squared on the bottom, I have L to the 4th on the top, so this is going to go away. This is going to become a 2. I've got 2 on the top and 4 on the bottom, so this goes away and this becomes a 2, and I get ml squared over 2. And so I go to justify and make sure, yeah, that's what they wanted. So here we go. We used integral calculus to arrive at that. Now this, of course, linear mass density is a little bit different than when we take a piece of a uniform rod, but it's no more complicated, and it actually integrates quite nicely. All right, so moving on to part B. It says the thin hoop shown here in this figure has a mass m, radius L, and a rotational inertia of ml squared. 3 rods identical to the rod from part A are now fastened inside this hoop. In part B, it says derive an expression for the rotational inertia of the hoop rod system about the center of the hoop and express all your answers in terms of m, L, and physical constants as appropriate. Now remember that when we find the I of a system is nothing more than the sum of the I of its parts. So what do I have? Well, this is going to be the I of the hoop plus, and you notice that they fasten inside the hoop 1, 2, 3 rods. But all these rods are identical, so they all share the same I that we just calculated. Or if I didn't know how to calculate, they tell me what it is, so I can use that here. So plus 3 times the I of a rod, because we have 3 rods in there. The hoop, they tell me, is ml squared, and the rod, we know from our calculations or from what they gave us, is ml squared over 2. So I end up with ml squared plus 3 ml squared over 2. Give them a common denominator, so 2 ml squared over 2 plus 3 ml squared over 2 for a grand total of 5 ml squared over 2. And that's the I of my system. Okay, moving on from there. In part C, it wants us to derive an expression for the final angular speed of the hoop rod system. So this is initially held at rest and held in place, but is free to rotate about its center, and a constant force is exerted tangent to the hoop for a time t. And we need to find that final velocity. So I'm going to write down what they tell me first. So many times with a physics problem, what you need to do is either draw yourself a picture, write down everything they've given you, or both, and in this case we're going to do both. So the first thing I know is I've got this hoop rod system, and I may not be the best artist at drawing this, but we've got this going on, and we exert a force tangent to the curve. Doesn't say where, just know that it's tangent to the curve. And I know that it starts at rest, so omega naught is 0. And it's going to act for a time t. So delta t is what it is, delta t, because we're going to leave everything in terms of this. And they want to know what is an expression for the final angular velocity of this. So this really is looking like, because if I got a constant force, I'll have a constant acceleration. So I'm really seeing a first kinematic forming here. And of course we're talking about rotation, so I'm going to use my rotational variables. My final rotational velocity is what I'm looking for. My initial rotational velocity is 0. I don't have alpha yet. And then that's delta t. So how could I find alpha? Well, I go to the fact that I'm getting a force exerted. And I know that torque is equal to I alpha. And I also know that torque is equal to RF sine the angle between R and F. So I can set this and this equal to each other. Now that happens a lot when dealing with torque. The only force that is torquing it is that force, so that is my one and only responsible party for this. I know R, that's the length of the rod. That's how I know the distance from here to here, because those rods are shoved inside this hoop. They also tell me the radius of the hoop is L. And I've gotten F, And since it's exerted tangent to the curve, it's sine 90. I just found I, and that I that I found was it 5/2? Yes. 5 ml squared over 2 times alpha. So now I can make sine 90 go away. I can get rid of an L here and an L here. And then I can multiply both sides by 2 over 5 ml. So that's 2f over 5 ml is equal to alpha. Now that's the alpha that I'm going to take, and I'm going to take it up here into this equation. So my final velocity is my initial velocity plus my acceleration times my time. And really, there's not much else I can do with that. 2f delta t over 5 ml. I didn't really have to even do this step, but that is as good as I can get that to be. All my letters check out. I'm allowed to use f, yes, delta t, yes, m, yes, and l, yes. All are on my list of acceptable variables, so we're going to leave it in that terminology. Okay, moving on. We change it up a little bit. This hoop is doing all sorts of things. This is why rotation lends so well to free response questions, because there's so much you can do with it. So this hoop is rolling without slipping, and it starts up with the angular speed that we just found, and it begins rolling without slipping up the ramp. On the figure below, draw and label the forces, not components, that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point which it is exerted on the system. So the very first force I think of is the force of gravity. That's by far the first force that I always think of. This is on a surface. Anytime anything's sitting on a surface, I think normal. I draw that there because it comes up. Remember, it's perpendicular. It acts at the surface. Now, there is a frictional force. That's why we roll. Okay, but which way is that frictional force going? Well, what you can imagine is this would slide up the ramp if it were frictionless. And so, because it doesn't slide, that frictional force is going to be pushing on it, and that frictional force is going to oppose that motion, and it's going to cause us to rotate. And so that is our frictional force as we're going on this hill. Okay, I was looking for my paper. I lost a paper that I had a minute ago. All right. So justify each of the choices of your forces that you just drew. Okay, if I'm going to justify these forces, this is my justification. This is II up here. Gravity is always toward the center of the earth. So down. Normal is always perpendicular to the surface. And friction opposes the desired slide, the desired motion. So as I'm going, this thing wants to slip as it goes. It wants to slip past, and so this friction is pushing it. That's why we roll without slipping. And so it would slip past and go on past and not roll smoothly were it not for friction going up this way. All right, lastly it says derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches the maximum height. Express all your answers in terms of m, l, I total, omega, and physical constants as appropriate. And I'll tell you, this part, when I worked this out before, this part was a little confusing to me as far as using the right things, the right variables that they allow me to use, because I wanted to sub in my total I, and then I didn't need to do that. So, you know, I tried to take it a step farther than I was necessary. So they want to know the height that this hoop is going to get to. Well, when you're dealing with that, anything that goes from down low to up high, or up high to down low, so we're going to go this way, I'm going to use conservation of energy. Okay, and so we're going to do K naught plus U naught equals K final plus U final. But at the bottom of my hill, my height is 0, so U naught is 0. So goodbye U naught. At the top of my hill, I stop. So my velocity is 0, so my kinetic energy is 0. So goodbye kinetic energy. And this is what I'm left with. So the kinetic energy initial, remember that it is rolling so the K naught is going to be 1/2 I omega squared plus 1/2 m v com squared. Okay, don't forget that we have to have both of those. So we'll start with them. It doesn't matter what order I write them in, so don't say, well, you wrote them backwards just a second ago. Does not matter. I'm leaving everything generic right now. We'll fill everything in a second. And then the final height is mgh. Okay? All right. So I get 1/2 m. Now this is where I'm going to get do a little bit weird. They wanted it in terms of omega. So if you remember that VCOM equals R omega, so omega is VCOM over R, and that's what we usually sub in, but this time we're going to sub in this one. So I'm going to put in R omega. I is the I total, and I know I, but I don't have to plug it in, is equal to mgh. Now, one more thing that I need to change, and that's this R, which is the radius, that's L. Now all I'm looking for is the height, so I'm just going to divide everything by mg. When I do that, this one, the m's cancel, so I get L squared omega squared over 2g plus I total omega squared over 2 mg is equal to h. And that's as far as I care to take it. I believe on the scoring guidelines they get it down to where you have 4 mg's on the bottom and then they combine the top, but there's no need to. I look at my list to make sure, let's double check that all these letters were on my list. L is on my list, omega is on my list, G is on my list, that's a physical constant. I total is on my list, omega again is on my list, M is on my list, and of course G is on my list. So that's the end of that one. And it looks a little crazy, but don't go thinking, well, I've got to make it look simpler than that, because if you get down and all you have left are the variables that they included on the list, then you're good and don't go any farther.